Hello everyone, welcome to my video on curve sketching. So now we're gonna put everything we've learned up until this point together into this topic. So this topic is gonna involve limits from the beginning, horizontal, vertical asymptotes. It's gonna involve derivatives, our first derivative test, second derivative test, all that combined in order for us to sketch the function from scratch. So let's go ahead and look at the strategy in order to solve these types of problems. So the strategy for curve sketching, first we begin by finding the domain of the function. So we're looking for the x values for which the function is defined. So that's step one. Step two, you're solving for the x and y intercepts. Okay, this is valuable information because it's giving us actual points that are on our graph. So recall that to find the x-intercept, you set y equal to 0 and solve for x. And looking for the y-intercept, you set x equal to 0 and solve for y. So let's just draw a quick picture just to remind ourselves. Let's say this is the function x, y. Let's say we have a straight line. Let me do this in green. It doesn't have to be a straight line or some function. Recall that this point here is the y-intercept. It's where it intersects the y-axis. And what do we know about this point? Well, we know this is the point 0, 0. So we know that this point here on the x, it didn't move. We're going straight up. So this point here is the point 0, comma, y. So we know that whenever we're looking for the y-intercept, you're setting your x with 0. Okay, that's what we have written here. Same for the x-intercept. Whenever you're looking for the x-intercept, notice it's on the x-axis. It's where it intersects the x-axis. And what do we know about this point? Well, from the origin, we only moved on the x-axis. We didn't go up or down. We didn't move on the y. So we know that the point here is x comma 0 because we didn't move on the y-axis. So we moved on the x, but we didn't go up or down. So whenever you're looking for the x-intercept, you're setting y equal to 0, and then you're going to solve for your x. Okay, so that's the idea. The next strategy that we're looking for is symmetry. So this is a new idea. Let's go ahead and write it. You want to know whether the function's even, odd, or neither. So let's write that down. Step 3. We're looking for symmetry. Is the function even, odd, or neither? So a function is said to be even if it is symmetric about the y-axis and satisfies the following equation: f of negative x equals f of x for all x in the domain. So if this equation is satisfied, this gives us symmetry on the y-axis, which makes our job easier when we're trying to sketch the function. Okay, so let's look at a quick example of an even function. So a function that's even is the function f of x equals x squared. Okay, how do we know it's even? Well, let's check to see if this equation is satisfied. Essentially what this is saying is, if we plug in negative x into the original function, do we get back the original function? Let's go ahead and try that. So if we have f of negative x, well, this is saying to plug in negative x into x squared. So we're substituting the x with negative x, and then we're squaring it. Well, what's negative x squared? Negative x squared is just positive x squared, because two negatives make a positive. And x squared is our original function. So we showed that f of negative x is equal to f of x. So this function here is in fact even. This is an even function. So if we draw this, we know what quadratics look like. This is the y-axis. This is the x-axis. So it looks something like this. So when we say symmetric about the y-axis, so this is our y-axis, it's saying if we fold it on the y-axis, the function is going to overlap. The first quadrant and the second quadrant are going to overlap. And that is absolutely true. And when we're trying to sketch functions that we don't know what they look like, well, knowing that it's symmetric on the y is very useful to us. So now let's look at the definition of an odd function. So a function is said to be odd if it is symmetric about the origin and satisfies the equation f of negative x equals negative f of x for all x in the domain. So what do we mean by symmetric about the origin? So let's first look at an example and consider the function f of x equals x cubed. Let's first show that this equation is satisfied. So whenever I'm checking for symmetry, what I do is I just plug in, I replace my x with negative x. So we look for f of negative x. Substituting your x in the equation here with negative x, we get negative x cubed. And if we do negative x cubed, which means negative x times negative x times negative x, that just gives us negative x cubed. So notice it's the negative of what we started with. We started with x cubed, and there's just a negative in front. That's what this is saying. So we do have symmetry. We have symmetry here, and we know that this function here is actually odd. This is an odd function. Okay, so we have symmetry about the origin. What does that mean? Let's go ahead and draw it. If we sketch, just quickly, if we sketch a x cubed function, what we get is something that looks like this. Okay, this is the function x cubed. How do we know it's symmetric about the origin? What does that mean? So essentially what you're doing is you're taking the first quadrant, you're taking the function there, and you're flipping it on, first you're flipping it on the x-axis, so you're bringing it down, and then you're flipping it again on the y-axis. So notice if you flip this down and then you flip it once more this way, then it's going to overlap. That's what we mean by symmetry at the origin. So we're going to essentially flip the function twice. We flip it once going downwards, or you can flip it on the y as well. If you flip this on the y-axis and then flip it on the x, notice that this function here is going to overlap. The function in the first quadrant is going to overlap with the function in the third quadrant. Okay, so that's what we mean by symmetric about the origin. And again, when you're trying to sketch functions that you don't know, it's good to know that you have symmetry. Okay, and if it doesn't satisfy either of these properties, where f of negative x does not equal f of x, or if it doesn't equal negative of what you started with, then it's neither odd nor even. Okay, so let's continue with our strategy. Okay, so the fourth thing that we have to do is check for asymptotes. So we saw asymptotes at the beginning of the semester. Recall, when we're looking for the vertical asymptote, we're taking the limit as x approaches some value to the left and to the right of some value a, and it's giving, the function's giving us plus minus infinity, so we have a vertical asymptote. Another way you could do it, we saw, is that if we substitute values directly, if we get a number over 0, we have a vertical asymptote, so we have to be careful for that. The second thing we have to look for is horizontal asymptotes. Again, so we saw this. We're taking the limit as x tends to plus minus infinity. If this value gives us a number, we have a horizontal asymptote, so we have to keep that in mind. Step 5, we're using the first derivative test. So again, this we saw in previous videos. So we're going to use the first derivative test to find the critical points, the local max and min, and the intervals for which the function increases and decreases. Okay, so we're going to create a table, put all this information down, and use it to sketch. Step 6, we're going to use the second derivative test. So we did the first derivative test, the second derivative test, to find the inflection points as well as the function's concavity. So here you could do the tables individually, but my advice is to put all this information into one table and gather all the information possible, and then once you have all this information gathered, we go ahead and we sketch. So a way to remember this strategy, because there's a lot of steps to it, is use abbreviation. So a lot of my students wrote this down on their test just to help them remember. Step 1 was the domain. So we look for the domain D. Step 2 was the intercepts, so DI. Step 3 was the symmetry, so DIS. Step 4, asymptotes, so DISA. And then it's the first derivative test, second derivative test. So for DISA, FDT, second derivative test, SDT. Once you finish with that, we sketch. And sketch. Okay. So let's go ahead and look at an example and apply this strategy. So here in our first example, we have to find all the pertinent information of the function f of x equals x cubed plus 6x squared plus 9x, and sketch the function, sketch the graph. Okay, so let's go ahead and do that. Finding all the pertinent information, that's the domain, intercept, symmetry, asymptotes, first derivative test, second derivative test, and then we'll sketch. So this is going to take up a lot of time. So let's go ahead and begin with the first step, domain. How do we find the domain? Well, what's the domain of this function here? We're dealing with a polynomial function. So there's no issues here. There's no division by 0, there's no logs, there's no square roots, there's nothing that we really have to worry about here. So this function here is defined for all values of x. So the domain x belongs to the real numbers. Okay. Another way you could write it is that x is an element of negative infinity to positive infinity. Both these notations are fine. So the domain is done. You could plug in essentially any x value here and there won't be any issues. Okay, so polynomial functions are well behaved. That's the domain. That's done. Next, what we have to do is go find the intercepts. So let's go ahead and do that too. Let's start off with the x-intercept. How do we solve the x-intercept? Well, we know we have to set y equal to 0. So take the original function and replace your y with 0. This gives us 0 equals x cubed plus 6x squared plus 9x. So how do we solve cubic functions? This is x to the cube, x to the 3. How do we deal with this? Well, we don't know how to solve cubic functions, but what we do know is that we could factor out an x. So by factoring out an x, you get 0 equals x times x squared plus 6x plus 9. Okay. Now at this stage here, we could use the zero product law. So we're multiplying two numbers and it's giving us 0. That means either the x is equal to 0 or the x squared plus 6x plus 9 equals 0. X equals 0, we're done. This over here we have to solve. So we have a trinomial, we could use product sum now. So using product sum, you're looking for two numbers that multiply to give you a times c, 1 times 9, which is 9, and the same two numbers to add to give us the number 6. Well, write down the factors of 9. The factors of 9 are 1 and 9, or 3 and 3. To get a 6, we have to use this pair here. 3, 3, 3, 3. 3 times 3 is 9, 3 plus 3 is 6. We got our roots. So we could rewrite this as x plus 3 times x plus 3 equals 0. So we could apply zero product law again, or you could rewrite this as x plus 3 squared. Both ways are fine, but let's use zero product law. So either x plus 3 equals 0 or x plus 3 equals 0, that's the same equation. Solving for it, we get x equals negative 3. Okay, so we don't have to do this twice. X equals negative 3. So we have an x-intercept at x equals 0, and we have an x-intercept at x equals negative 3. So we'll keep that in mind. So we know it's gonna, this function here, this is really valuable information. It's telling us that it's gonna pass through these 2 points. It's gonna pass through the point, this one here, it's x is 0, y is 0, because it's the y-intercept, our y is 0. And we know it's gonna pass through specifically the point negative 3 and 0. That's huge information. Okay, so we'll keep this on the side. The next one we have to go find is the y-intercept. Let's go find the y-intercept. How do we find the y-intercept? Well, the same idea. We set x equal to 0. Replacing your x with 0 in here, we just get f of x equals 0 cubed plus 6 times 0 squared plus 9 times 0. All the terms have a 0, so everything is cancelled. We get f of x equals 0, or y equals 0. And this point here, we actually knew already, because we knew when x went through 0, y is 0, so it didn't really give us any information, but that's all right. So 2 points that's definitely going through due to the intercepts is the point 0, 0, and the other point negative 3, 0. So we'll keep that in mind. Let me just erase and give us space, and we'll continue with the problem. Okay, so I'm just keeping it here on the side. We have our domain is x is all real numbers. We have the 2 points that it's passing through, 0, 0, and negative 3 and 0 are x-intercepts. So the domain's done, the intercept's done. Next is symmetry. So let's go ahead and check for symmetry. This is step 3. Okay, so let's check if the function's even or odd. For even, well, essentially what I do is right away I go solve for f of negative x. I think that's the best way to solve these problems, because if it gives us the original function that we started with, it's even. If it gives us negative of what we started with, then it's odd. And if it doesn't give either, then it's neither. It's neither even nor odd function. So going and solve for f of negative x is the best way to do this. Okay, so let me erase even. We're essentially doing both cases in one shot. So we have f of negative x. So substitute negative x into the function here. We get negative x cubed in brackets plus 6 times negative x squared plus 9 times negative x. This gives us negative x cubed plus 6x squared minus 9x. Okay. Is this negative of what we started with? Because we started with x cubed plus 6x squared plus 9x. So it's definitely not even, because it's not the exact same function that we started with. We have a negative here, here it's positive. We have a negative here, it's negative. But is it negative of what we started with? Well, what we could do is factor out a negative. If we factor out a negative here, divide everything by negative 1, let's say, we get x cubed minus 6x squared plus 9x. Is this negative of what we started with? Well, no. Look at the negative 6x squared. Here it's positive 6x squared, so it's neither odd nor even. Okay, so there's no symmetry. So let's go and move on to asymptotes. Let's look if there's any horizontal and vertical asymptotes. So here we have our asymptotes. I wrote down null symmetry. So asymptotes, horizontal, vertical asymptotes. Let's start off with vertical asymptotes, which I abbreviate VA. Looking for the vertical asymptotes, we're essentially looking for a division by 0. But the function that we're dealing with is a polynomial. There's no division, there's no fraction. So there's no issues with this. We know the functions, the domain of the function's x for all real numbers. So there's no vertical asymptotes because it's defined for all real numbers. So it wouldn't make sense for there to be a vertical asymptote because then the function wouldn't be defined for all real numbers. It would be a value for which there's a vertical asymptote where the function, there's a point that's not defined, right? So the vertical asymptote, there's none. Okay. Next, we could check for the horizontal asymptote. How do we check for the horizontal asymptote? We take the limit as x goes to plus minus infinity. So let's go ahead and do that. We're taking the limit as x goes to positive infinity of this function here. (6x squared plus 9x). And substituting all the x with infinity, just infinity cubed plus 6 times infinity squared plus 9 times infinity is just infinity. It doesn't stop at a value. This just takes off to infinity. Same for negative infinity. We're just going to get, we won't actually get a number. We won't get a value. It's going to be a plus minus infinity. Therefore, there's no horizontal asymptotes. Okay. Because we have a horizontal asymptote if this gives us an actual value. In this case here, it's going either to plus minus infinity, so there's no actual horizontal asymptote. Okay, so asymptotes in this case, there are none. Let's move on to the next step, first derivative test. So next we have the first derivative test, FDT. Let's go ahead and start off by finding the critical points. So we take the derivative, set it equal to 0, f prime of, we'll call it c. Taking the derivative of this, we get 3. Instead of x squared, I'm going to write c squared plus 12 times c plus 9. Okay. We take the derivative and we set it equal to 0. This is the critical numbers or critical value. That's what we're looking for now. Here we could factor out a 3. Let's go ahead and do that. Factoring out a 3, we get 3 times c squared plus 4c plus 3 equals 0. Now we can use product sum method. So multiplying two numbers to give us 1 times 3, which is 3, and those same two numbers that add to give us 4. So the only factors of 3 are 1 times 3. So it has to be this combination. 1 times 3 is 3, 1 plus 3 is 4. We found our roots. So we could split this up to 3 times c plus 1, c minus, plus 3 equals 0. Now we use zero product law, so either 3 equals 0, c plus 1 equals 0, c plus 3 equals 0. 3 cannot be equal to 0 because it's just a number. Here we have c plus 1 equals 0 or c plus 3 equals 0. Bringing over to 1, bringing over to 3, we get c equals negative 1. That's our first critical value. And c equals negative 3. That's our second critical value. If you want, you could have used a quadratic formula here, but I always insist on using factoring methods. It's quicker. Okay, you don't want to use quadratic formula. It's just going to take up a lot of time. So we have our two critical values here. Now we create our number line and see the interval for which it's increasing and decreasing, and at the same time we have to identify whether at these critical values do we have a local max or a local min. That's our job, or a saddle point. So let's go ahead and do that. Let me erase. Critical values. So creating our number line, we have negative 3, negative 1, let's say 0 would be here. Let's box these guys in. So here I'm going to take the first derivative, and then here I'm going to put the original function. What does it tell us about the original function? So let's put our test values. So here, this is our critical point. This is our critical point. And now we're going to test values in between. So to the left of negative 3, we'll take negative 4. In between negative 3 and negative 1, let's take negative 2. And bigger than negative 1, we'll take 0. Okay. So let's go test these points. The values in green are our test points. and we'll plug them into the first derivative. So again, I shouldn't have erased the first derivative. Let's put it back on the board. The first derivative was f prime of x, which is 3x squared plus 12x plus 9. Okay, this was our first derivative. You don't have to factor out the 3, we could use this as is. So let's go ahead and plug in our test points. So we'll test out f prime of -4, f prime of -2, and f prime of 0. Okay, so starting off with 0, it's easy. I'm just going to plug in 0 here. We get positive 9. So again, we just care about the sign. So this was a positive value. When we plug in -2, what do we get? This is going to turn out positive. So 3 times -2 squared plus 12 times -2 plus 9. This is 4, 12, and this is 9. So here we're going to get -3. We're going to get a negative value. That's what matters. So we get negative, I believe it's -3. And then if we plug in -4, let me take a calculator not to make a mistake. And we'll plug in -4 in here. So we get 3 times -4 squared plus 12 times -4 plus 9. So I got a positive value, positive 9. So it's positive. Let me just ensure that this is actually negative. So 3 times -2 squared plus 12 times -2 plus 9. Yeah, -3. Okay, so we're good. So we got positive, negative, positive, which means the original function here, because the first derivative is positive, the function is going to be increasing. After that, in between -3 and -1, it's going to be decreasing. And then after that, it's going to be increasing on the interval from -1 to positive infinity. Okay, this is our number line. This goes to infinity. This one here goes to negative infinity. Okay. So let's write down the information that we have. So it's this. So what we determined is that at the critical point -3, or a critical number, we have a local max. Why is it a local max? Well, it went from a function that's increasing to decreasing. So it's increasing to the left, decreasing right after. That has to be a max. So think of it as like follow the arrows and we get the top of the hill, let's say. Here we're going from a valley, then it's going up. So since it's decreasing to the left, increasing to the right, it's going lower than up, and then that means we have a local min at -1. Okay. And we have the interval for which the function is decreasing. So let me write this down. It's decreasing on the interval from -3 to 1. And it's increasing on the interval from -infinity to -3 union -1 to infinity. Okay. So we found the interval for which the function increases, decreases, and we found that at -3 we have a local max, and at -1 we have a local min. Now let's move on to the second derivative test. So now we move on to the last step, the second derivative test, SDT. So we finished the first derivative test, we're doing the second derivative test. I just want to mention, I think I wrote decreasing from -1 to +1, -3 to +1. I meant -1. So it's decreasing on the interval from -3 to -1. I apologize about that, because our local min was at -1. So now let's do the second derivative test. What do? We take the derivative twice and we set the function equal to 0 to find our inflection points. Let's go ahead and do that. So the first derivative we had was 3x squared plus 12x plus 9. Well, the second derivative is 6x plus 12. That's gone. Set this equal to 0. We get 6x equals -12. Divide by 6 on both sides. We get x equals -2. Okay. So we have an inflection point at -2. Okay. Or a potential inflection point. We don't know, because we have to check the concavity and ensure that the concavity to the left and to the right changes sign. If they don't change sign, then it's a saddle point, so it's not actually an inflection point. So a potential inflection point at x equals -2. Okay. So let's go ahead and draw a table. So as I mentioned, I would do the first derivative test and the second derivative test at the same time. Here I'm doing it individually. I created my table for the first derivative test. On an actual exam, if I were in your shoes, I would actually put everything on one table. Don't do two tables, it takes more time. If you could save time, because already this problem is long, you could save time by doing everything on one table. That's the way I would do it. So an example of what I'm talking about is, we'll do it like this. When I'm creating my number line, as we saw before, I wouldn't do it only for the first derivative test. I would put both my critical values and my inflection points on my number line. So from before, our critical values were -3, -1. And now we know the inflection point that we just solved for was at -2. Okay, so I'll call this an IP, an inflection point, and I'll call this a CP, a critical point. Okay, and what I would do is test values in between all these terms. Okay, so instead of doing what I did in the step 5, the first derivative test, I would do it all together as I'm doing it now. So put my critical points and my inflection points. Let's go ahead and do the table. So the table is going to look something like this. 1, 2, 3. Okay. So I put my first derivative here. Let's put this a bit further. My second derivative here, and then the original function on the bottom. Okay, so we're going to look at the first derivative, the second derivative, and see, combine, what does that tell us about the original function. So let's go ahead and do that. Let's test values over here. So to the left of -3, let's test with -4. To the in between -3 and -2, let's test with -2.5. In between -2 and -1, let's test with -1.5. And here, bigger than -1, we'll test with 0. So when we're testing, you're plugging into the first derivative and again also into the second derivative. Okay, so we did already the critical points. So we knew that when we plugged in -4, we got, from before, this was, if not, you would have to actually plug in -4 into the first derivative, but having done it already, we got this was negative, this was positive, positive, and then this was negative. Oh, sorry, it was the opposite. So it's increasing on negative. Sorry, this is positive, negative, negative, and this was positive. Yeah, it was decreasing on the interval from -3 to -1, increasing. Okay, perfect. So this was done on the previous step, but I would do it now. So if I were you, I would plug in -4, -2.5, -1.5, and 0 into the first derivative to get these values. Okay. Next, let's plug in the second derivative test. So looking at the second derivative test, all we really care about is the inflection point at -2. So take a value to the left, take a value to the right, because it's going to be the same concavity to the left and to the right of the inflection point. So you don't have to actually test at -4, -3, and -2.5, let's say. You could just test to the left, any point to the left of the inflection point. So take any point that you want, -4, -3, and plug it into the second derivative. Okay, so again, I erased the second derivative. Let me write it down. The second derivative was, I believe, 6x minus 12. No, 6x plus 12. Yeah, so it's 6x plus 12, and we're going to plug in a value to the left. So let's plug in, choose any point to the left of -2. I'm going to take, I don't know, -4. So f double prime of -4 is 6 times -4 plus 12. This is -24 plus 12, which is -12. We know it's negative. So to the left of it, we're getting a negative value. Okay. So to the left of -2, we're getting a negative value. And let's see what happens to the right of -2. So let's take the value to the right of -2. I'm going to take 0, because it's just easier to test with. So taking 0, plugging into here, we get 6 times 0 plus 12, giving us positive 12. So this is positive, this is positive. Since it changed from negative to a positive, this is in fact at -2, we do have an inflection point. So the concavity is going to change. Okay. So let's do the next part. What does this mean about the original function? This is why I do everything on one table. Okay. So essentially what we have is a U and an upside down U when we're talking about concavity. This or this. Okay. So here, we're going to combine what we have from the first derivative and the second derivative to see what happens on the real function. So the first derivative here is positive. That's telling us that the function is increasing. Okay, so it's increasing, and we know it's concave down. So this over here, remember concavity, if it's concave up, it's smiling, it's a positive percent. If you're positive, you're smiling. This is concave up. This example here is concave down. So it's like a frown face, you're sad. If you're negative, you tend to be frowning. So here it's increasing and concave down. So we're on the concave down, we're looking here, and which half is increasing? So we're on this one here because it's concave down. The second derivative was negative, but the first derivative was positive. We're looking at this side because this function's increasing. This side of the, let's say the parabola, it's increasing and it's concave down. So our original function is going to look something like this on this interval. From negative infinity to negative 3, it's going to be increasing but concave down. If we look over here, the first derivative is negative, the second derivative is negative. So since the second derivative is negative, it's concave down. So again, we're looking at concave down, but the first derivative is negative, meaning that the function is decreasing. So we're now using this half of this drawing because it's concave down and it's decreasing. From left to right, we're going down. So then it's going to continue over here and go downwards. That's what this is telling us. Now if we look on this interval from negative 2 to negative 1, the function, the first derivative is negative, so it's decreasing again, but the concavity is upward. So we're looking at this drawing here. So we're concave up because the second derivative is positive and it's increasing. Which half are we using? Are we using the left half or the right half? Well, we're using the right half because it's increasing. From left to right, we're going upwards. So after this, it's going to look something like concave up and something like this. And then over here, to the right of negative 1, it's increasing and it's concave up and it's increasing. Oh, sorry. This is wrong. First derivative is negative, the second derivative is positive. So it's concave up and it's negative, the first derivative is negative, so it's decreasing. So we're using this half over here, to the left of it. So we're going down and to the right. Okay. And then lastly, it's increasing, the second derivative is positive, the first derivative is positive, so it's increasing and concave up. So we're using this half. Okay. So this is what our original function is going to look like on the intervals in between our critical points and inflection points. Okay. Now with this information, we could sketch the actual function. So let's go ahead and do that. So the next step that I would do, I would go ahead and find the actual points where we have our local min or local max and the inflection points. So let's go ahead and do that. So we know when x was at negative 3 that we had a local max, but what's the actual point? So let's go ahead and find that by plugging in negative 3 into the original function. So f of x, or f of negative 3, equals negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3. This gives us, let's do it on the calculator, negative 3 cubed plus 6 times negative 3 squared plus 9 times negative 3. So this gave me a value of 0. Okay, right, we knew that already. Negative 3 and 0 was here. Let's check at negative 1. So negative 1 cubed plus 6 times negative 1 squared plus 9 times negative 1, giving us negative 1 plus 6 minus 9. This gives us negative 4. So we have a local min at the point negative 1 comma negative 4. We have our local max. Sorry, yeah, this is a local max. This is a local min. Okay, and lastly, let's go check for the inflection point. Where's our inflection point? Well, it's at negative 2. So let's go find the associated y value. So negative 2 cubed plus 6 times negative 2 squared plus 9 times negative 2. That gives us negative 8. Positive 4 plus 24. 9 times negative 2 minus 18. Okay, so this gives us 6, negative 2. So this is the point negative 2 comma negative 2. That's where we have our inflection point. Okay. Using all this information, now we're ready to sketch the function. So when you're doing this, remember, use a ruler. I'm not using a ruler, I'm just using this by hand, but you should be using a ruler. Next, what we have is, let's put on the graph the points that we actually know. Starting off with the intercepts. We know that the x-intercept is at 0, 0, and negative 3 and 0. That means the function is actually passing through these points. Let's go ahead and write them. So the first point is here at 0, 0. And then we have negative 3 and 0. So let's go somewhere over here. Negative 3 and 0. Our function is absolutely passing through these 2 points. That's valuable information. Let's keep going. So we did this. There's no horizontal asymptote, there's no vertical asymptote, and we know that it's defined for all x values. We don't have to worry about symmetry, there's no symmetry here. So let's move on. Now what we're going to do is identify where the local max, the local min, and the inflection point occur. So we know that there's a local max at negative 3 and 0. This is a local max. We found this from the second derivative test on our table, negative 3 and 0. And we stated that at negative 1 and negative 4, we're going to have a local min. So that's another point that the function is going to pass through. The point negative 1 and negative 4, let's say around here. Let's say this is negative 1. Let's say this is negative 4. It's not drawn to scale, but this is our local min. Oh, sorry. Let's write local min. Okay. So we're going to pass through these points, certainly. And lastly, we have our inflection point, where the concavity changes. This occurs at negative 2, which would be around here, and like negative 2, which would be like halfway here. So at this point here, this is the inflection point. Okay, I'll call it IP. And now with this information, we're ready to sketch. Because if you refer back to the second derivative test when we created our table, we know that on the interval from negative infinity to negative 3, it was increasing and concave down. So the function looks something like this. Okay, so it was increasing and going to the right. Then we saw from, again, our table that the drawing was on the interval from negative 3 to negative 2, it was decreasing and concave down. So from negative 3 to negative 2, it's concave down and decreasing. We now hit our inflection point. Then again on the table, we saw from between the interval from negative 2 and negative 1, it was concave up and decreasing. So something that looked like this. And then lastly, from negative 1 to positive infinity, it was concave up and increasing. So it looked something like this. And at the same time, it has to pass through the origin because that's an x-intercept. So it's going to look something like this. And this is the sketch of the function f of x equals x cubed plus 6x squared plus 9x. So congratulations, you did this without the use of applications, computer application softwares. You did this all by hand. You can see it's very difficult. There's a lot of work to do. But this is an example of a curve sketching problem. So I hope this helped. We'll keep practicing, and I'll see you in the next video.